All right, well, good afternoon, everyone. We're going to continue talking today about constitutive models that take into account elastic and plastic deformations. And in order to accompany the theory, we're going to work in a problem of compaction of muddy sediments. So a muddy sediment will be a sediment that is usually uncemented, and it has a variable composition of sand and clay. As you can see in this plot, as a function of depth, we have an offshore sediment. This is actually in Gulf of Mexico, offshore Louisiana, lots of oil over there, and this example comes from there. So as you get to the seafloor, you start to see sediments, and you can see that by interpreting this log, which is called a gamma ray log, basically the more gamma ray emission that you measure, the more clays you have in that sediment. And based on interpretation of this, probably some other well log tracks, you can tell what is the percent of sand by volume. And in this particular example, you can see that as you go deeper, the percent of sand decreases, which means that as you go deeper, you have more clays and less sand. So for example, at the point like this, the percent of sand is just 10%, and the rest is all clay and silts. So this one will be something closer to, how would you call this in the geotech vocabulary? More sand than clay. And let's say it will be a clay sand, right? And this one? A sandy clay. So that's usually the way that these sediments are called. So, and this is important, okay? This is the way that you refer to these mixtures. This is a clay sand, but it's a sand. And this is a sandy clay, but it's mostly a clay. Yes?
So is the change in composition responsible for the deviation from the normal compaction trend you find around?
Yes, exactly. And that's where we want to get to right now. Yes, Steve?
Is this equipment accurate enough to identify which part is sand, which part is silt, which part is clay? Between sand and clay you have silt.
Yeah, well, no, here you couldn't tell much about the silts. You have to do something else to tell how much silts you have. But this measurement of gamma ray, it's for clays. It's not for silts. All right, so let's look at the third track that we have here. It's measurement of porosity as a function of depth. And as we have discussed before, the deeper you go, the higher the effective stress you should expect, because the density of water is, say, 1, and density of sediments is 2.4. So the deeper you go, the bigger the difference in effective stress is going to be. And because of that, you should expect lower porosity. But look, here the actual measurements of porosity that you see are that the porosity starts to decrease, but some point it doesn't follow what we call a normal compaction trend. And that's something we're going to discuss a little bit today, and it's related to the constitutive model. But instead, you see that this departs from that normal compaction trend. And based on that departure, I'm going to ask you to compute what is the expected effective stress to obtain this porosity, and based on that expected effective stress, what the actual pore pressure is, right? So in here, if this is porosity and this one is effective vertical stress, you would expect the porosity to decrease with effective vertical stress. That's what is called a normal compaction trend. And usually it's a non-linear relationship. And if you go a little bit lower here in the page, you see that you have two possible equations to explain that relationship. Sometimes this one works better, some other times this one works better. But it's the same thing. It's a non-linear relationship between porosity and effective stress. So in this case, if porosity is not really going down, as we see over here, as expected with depth, that means that effective stress is not decreasing either. And if this is not decreasing, we know that total stress is increasing, but probably pore pressure is not, is increasing more than expected. And that's what is going to lead in this section to what we call overpressure. And overpressure means that the actual pore pressure is higher than the hydrostatic pore pressure. And this is what I want you to calculate based on these principles. So with all this data, you're going to have to digitize this plot. I'm not going to ask you to digitize everything, okay? But at least about the 20 points. Out of that, you're going to be able to plot a trend for this normal compaction part for the region in which you expect a relationship between porosity and vertical effective stress. And based on that trend, you get the expected pore pressure out of these points. And basically after that, what you can do is you can plot pore pressure. So let me see, I think it's in the next part. So at the end, all I want you to do here is to have a plot of porosity, something that you already have, but this is a digitized version. Porosity as a function of depth. Here, vertical stress as a function of depth too. You're going to see that if this is your expected hydrostatic pore pressure, your actual pore pressure in the region of the clay sand is going to follow that, but then it's going to start to deviate. And that's going to be the actual pore pressure. And the third plot that I'm asking you here, it's a plot of what is called the overpressure parameter, where overpressure parameter is defined as the pore pressure divided by the total normal stress. And this is going to look something, it's defined for the sediment part. It's going to be hydrostatic, and then it's going to increase. What is the maximum value of the overpressure parameter? What would you expect? 1? Why 1? Because the pore pressure cannot be higher than the vertical stress, right? And if we have a case of normal faulting or strike slip stress regime where the S3 is SH mean, the pore pressure cannot be higher than the value of minimum total horizontal stress. Okay, so our job today is going to be to see how we use these equations, how they come into the constitutive model, and how we use that later on to predict the elastoplastic response of a material with this type of camp clay constitutive model. Okay? So we'll come back to this in a minute. Yes, John?
Are those porosity readings on the right plot from just taking samples at various depths, or are they?
No, many of these porosity readings, they come from also another types of well logging measurements. So very likely it comes from what is called the neutron log, or probably it might come also from the density log. It might come from another log, which is resistivity, or from another one that would be the sonic or the P-wave log. With all of these, you can get an idea about porosity. I'm not remembering exactly in this case what they used, but usually it's a combination of many of those. Sometimes you can also use samples to help calibrate a little bit your equations, because all of those are equations, and they don't mean to be, or they are not necessarily all the time very accurate. So with the actual measurement, you can calibrate those. It's really hard to sample sands. But remember, in this case, this is porosity of a mix of sand and clay. But if you want to measure porosity of sands, you have to do it in situ. Otherwise, as Michael says, it's almost impossible. Or you have to freeze it. Yeah. All right. So let's continue talking about the critical state of soil mechanics model, and about that one, about the camp clay model. So last time we saw that if we want to draw the stress path of a triaxial test in this PQ space, that's going to have a slope of 3 to 1, Q over P. So let's do that. Let's run a triaxial test starting from this point. All right? So I'm increasing stresses in all sides. There is no deviatoric stress. So I move from here to there. And now I start increasing the deviatoric stress. So I go from here, past that line, and over that point. All right. So what you would expect to see in this case, it will be something like this. This point is going to be very important. So let me extend the line out of here. And this one is going to be also an important point. What did we say it happens when you go over the shear line for a Moore-Coulomb criterion? You have failure for the Moore-Coulomb, but this one is a little bit more complex. What about the strains?
So everything up until the criterion is going to be elastic, everything past it is going to be plastic.
Okay, so this is going to be straight line. This is Q. This is the strain in direction 1. So this is going to be straight line. Then we get to that point. What happens after that? And notice that here too, elastic, I compress. So this is going to be a positive volumetric strain. All right. What happens after that? What? It continues. It's going to go over that line. And if I get to that point, you remember what the Moore-Coulomb criteria would say? That we'll have, what will happen to volumetric strain? Dilation, right? So if we pass that line, we're going to have dilation. And in this case, what we will see is that as we pass this line, now we're going to get into in the plastic region, and this is going to look something like this. going to start to bend, and then it's going to reach a peak, which is going to correspond to this, and then it's going to come down, and it's going to go into an asymptotic trend. So we can go up to there, we can pass that line, but we're going to be limited by this failure surface. And after this, you go down and you come back to that point. This is the typical response of what is called a strain softening material. And let me do that also with green. So this is a line, and then this starts to curve, reaches a peak, and then goes down. And it's called strain softening because as you apply more strain, the strength of the rock tends to decrease with strain. So it reaches a peak, and then it gets weaker. So this is called strain softening. And also with the volumetric strain, we will see that the material will start to shrink, but at some point, when we get here, that trend is going to change. And let me draw also an asymptotic value. As we go over that hump, the material is going to dilate. So all of this region is dilation. Notice that the change in volumetric strain is negative, which means that it's a dilation. We assume that positive changes are contraction, negative changes are dilation. So probably you have seen materials like this already, and this is typically sometimes the case also of a cemented material. It goes over a peak, and then it might have some what is called residual strength. Notice that the material comes back to this point where the stress path hits the critical state line. So as it approaches that asymptotic behavior, it doesn't change anymore. Because it doesn't change anymore, that's why it's called a critical condition. Because it approaches that point and doesn't move from there anymore. Touches the critical state line and it stays there. All right. Yes?
When we first hit critical state line, it deviates from the linear line, the stress curve.
Yes, because
You said the circle, the eclipse is initial yield surface. So in this case, then initial yield criterion is critical stress line.
yes. Yes, that's where you start to see.
It is the peak stress that is
This line is going to limit the attainable state of stresses, the failure surface, and this is going to be the yield surface because at that point you start to develop plastic strains. So we're getting into a more complex model now, but I would say, let's try to do. We have one more case, and let's try to see the difference with the other two models. All right. So this kind of test, this is a strain softening response, and sometimes this is something that is called the dry side of the failure part. And it's called dry because if you were to have a, let's say we're working with the sand. If you have dilation, as you dilate, your pore space will tend to be bigger and will tend to suck water. Can you see that? So you have sand, and now the pore space suddenly becomes bigger. In order to fill up the pore space with water, more water has to come into the material. So this will be to the right of this point. Notice that this point now is very important, because whenever I have a stress path that goes to the left of this point into the dry side, I'm going to have this strain softening behavior. Let's now run a test that goes through the wet side. So this is going to be, if that's the dry side, this is going to be the wet side. And let's say that we have stress path also with a triaxial test that starts at this point and goes in this direction. So notice that now we're starting at a much higher mean stress. We put a lot more of stress around the sample, and we load it deviatorically to failure. What would you expect to see in this case in the strain response? I'm going to extend this plot, and similarly as before, you will see a linear start up to the point that you get more or less to the yield cap, which is somewhere over there. And once you get in there, you pass the yield line. So now this one is the yield line. It's where you start to see plastic strains. At that point, you will start to see that this one starts to bend over, and it will reach an asymptotic trend to that condition. So it's like this, and then you start to have plastic strains, and it reaches an asymptotic behavior like that one. Notice that again, as you pass a line, then you start to have some plastic strains, and you also tend to an asymptotic trend. And once you get there, the condition also does not move anymore. It just stays at that point. If this one was called strain softening, how is this material going to be called? Strain hardening, right? And what that means is that the material gets harder and stronger as you apply more strain. And if we were to look now at the volumetric strain, what do you think will happen with the volumetric strain? Is this one going to dilate? It doesn't dilate. It always contracts. And it will first compress elastically up to a point where you reach the yield cap, and starting at that point, it's just going to tend to a constant value. And at that point, it's not going to change volume anymore. So this is the same. This is the slope 1 to 3. And basically, this is the behavior that we want to capture. The same material, depending on what it is its initial stress, it can be either strain softening or can be strain hardening. It depends, the same material, starting at the same conditions, it depends how it's going to deform if you go into a triaxial stress path, or as we're going to see in a bit, if it goes to a uniaxial or olumetric stress path, that is going to be like that. It's going to go in this direction. So depending on in which direction you go, you can have a different stress strain response. Any questions so far? Let me see if I forget something. Let me add something over here. Remember that with this yield surface, the plastic strains are going to be, this is a vector normal to that yield surface. We're going to have a deviatoric plastic strain. It's going to be that vector, and this one is going to be the deviatoric volumetric strain. Okay. Yes, Steve.
So one question.
Yes.
So for the second condition, for the west side,
Yes.
you unload it after it's reached the CSL, critical state line. So it will go back on the critical state line, right?
So if you were to unload it, yes. I have an example about that with now loading and unloading that we can take a look at. And it is called the wet side, that one, because if you were to follow that path, and you will constantly, your porosity will get lower and lower, and it will tend to expel water if it's under drain condition. All right. Also related to this is something which is called, it's a word which is mostly used in the rock mechanics vocabulary, something called brittle to ductile transition. And it's something which is naturally explained by this kind of constitutive model. What that means is that if you have the same material, you may test it at a low confining pressure, and you will see something like this, where this is sigma d and this is epsilon axial. So I'm running here a test like this. It could be triaxial too. But if you have low confining stress, you may see something like that. As you increase your confining pressure, you will see something like that. And eventually, if you increase it a lot, you will see it will never reach a peak stress. And this will be as you increase your sigma 3. Such behavior is called a brittle to ductile transition, because it goes from something that looks brittle, that breaks very quickly, to something that looks more ductile, in which you can maintain a lot of stress even though you have a lot of deformation. And one of the factors that makes this brittle to ductile transition, which is very well captured in our Gamplay model, is the mean stress. The higher the mean stress, the more ductile the material behaves, right? Imagine if we were to run a test that starts right here and goes exactly to that point, it will go like this and then be perfect plastic. So we see something similar to what we see over here. But that's not the only factor that makes a brittle to ductile transition. Some other factors, can you think about any factor that would make this brittle to ductile transition?
Well, we talk about ductile to brittle.
Brittle to ductile, yeah.
But no, I'm saying we talk about the opposite, ductile metals.
Oh, okay.
Brittle due to temperature and material science.
Correct, correct.
Guess temperature.
Temperature, it's a very important factor, especially when you go deeper in the subsurface, and as you get, several kilometers, material gets very hot, and the properties are not the same that under our ambient temperature. So, and if you go very deep, then you find like magma, right? It's not solid. It's ductile. What else? Any other thing that you could think of? but porosity will be the same thing as P. So it's they're both linked. What? But that's also here. It's also here. Well, the other example I have, it's not very easy to figure out, and actually it took me a lot of time to think and understand that. But it's also another factor. It's scale, length scale. So let me explain that. So we say other factors for brittle to ductile transition. Rates also too. I forgot about rate. So we say temperature, loading rate, and loading rate, remember this is linked to viscoelasticity, and also length scale. It may not happen for all kind of materials, but particularly in fractured rock masses, what you tend to see is that you could have a very large fractured rock mass with fractures, and it is not the same to do a test on a piece of rock without fractures than to do it in a piece of rock with fractures. What kind of a stress strain response do you think I'm going to get in the intact rock? It doesn't have any fracture inside. It's very well cemented. As soon as you pass the peak stress, it's gonna make a loud noise like boom, and then go down. However, the fractured rock, it has mostly strain controlled by fractures and by frictional strength. So if at the constant confining pressure or minimum effective stress, you will load it, probably it will be softer than this, and you will load it and it will just reach some constant value, which is the residual strength of the fractures. Yes, Robert.
Is it length scale though, or is it just it's the presence of fractures? If you had so let's say if you cut your smaller sample in an area where there were fractures,
Yeah.
would it behave the same as the larger sample with fractures?
Probably my statement is accurate for geologic materials, because for geologic materials you tend